In this video, we'll be looking at a special kind of recursion strategy called use it or lose it. And we'll take a look at this strategy using an example where it's particularly effective. Suppose we have a handful of coins. Let's say we have a 1-cent piece, a 5-cent piece, a 10-cent piece, and a 25-cent piece. And then suppose we had some target amount. Let's write the exact change function to see if we can reach that target amount using the coins that we have in our hand. This function will take two parameters. The first parameter is a list of integers representing the worth of each coin we have in our hand. And the second parameter is the target amount that we want to make change for. So let's say we called exact change using these coins that we have in our hand and a target amount, say 15 cents. Now the question is, can we make 15 cents from these coins in our hand? And the answer is yes. We can make that amount by just grabbing the 10-cent piece and the 5-cent piece. 10 plus 5, 15. Now say we wanted to see if we could make 13 cents from these coins in our hand. Could we do that? The answer is no. We have a 10-cent piece and we have one 1-cent piece, but we don't have two more 1-cent pieces to make a total of 13, which would be 10 plus 1 plus 1 plus 1. But we only have one of these, so we can only make 11 cents. Now we'll see how this function translates into what we'll actually see when we create this function.
But how are we going to define the exact change function? Just like with recursion, we'll want to choose our base cases, our smallest forms of the problem. Remember, since base cases can't be broken down at all, we have to handle the base cases before we try to reduce the problem. If the target amount of change is 0, regardless of the coins we have, we can make change easily. We just don't do anything. So let's go ahead and return true if our target amount is 0. If we still have change left to make, on the other hand, but we don't have any coins, it's impossible to make change. So let's return false in that case. Now that we've got our base cases covered, let's move on to the signature part of use it or lose it. We know that if we have more coins, we've got ourselves a harder problem. So let's go ahead and trade our problem in for an easier problem with fewer coins. Let's say we're trying to decide if we should use the first coin in our list or not. A way to make our problem smaller is to first assume that we use that coin, then determine whether it's possible to make the remaining amount of change with the remaining coins. Let's call this our use it result. So, as you can see, we set use it equal to a call to exact change where we've reduced our target amount by the first coin, and we reduced our coin list to everything but the first coin. Now, let's go on to the lose it case. The lose it case is even simpler. What we're going to do is we're going to make another call to exact change, but this time, instead of using our coin, we're going to lose it. So, we set lose it equal to a call to exact change without changing the amount this time, but still removing the first element of our coin list. Then, to bring our two results together, we want to see what happens if either lose it works or use it works. And if either of those work, we want to return true. So the operator we have in that case is OR. So if use it is true, we return true, and if lose it is true, we return true. So, to break it down one more time, for use it or lose it, we have a set of things we're considering using to solve a problem, only some of which we'll need. First, we check to see if we're at one of our base cases and can solve the problem immediately. But if not, we see what happens if we use the first element in our list. Then, we check to see what happens if we don't. Then, recursively continue from each. If either of those work, either using it or not using it, we return true. Now, if you've followed along with the reasoning so far, but still don't really understand why use it or lose it works, don't worry. We're going to look at some visualization to kind of see what the computer is doing and get a better understanding of how use it or lose it works. So, we've got our call to exact change with 15 cents that we're trying to make, and our coin list of 1, 5, 10, and 25. And we're going to break it down into our two cases. On the left, we have our lose it case, where we've gotten rid of our 1 cent piece, but haven't changed the amount. And on our right side, we have our use it case, where we've reduced the amount by the appropriate coin value. Remember, this is recursive, so each call will continue making 2 calls until it finds a base case. So, that continues, branching into 2, and each of those continue, branching into 2. And, eventually, we find a base case. Here, on the right, we have 0, our target amount, and a coin list with 25 in it. But we don't care about the coin list, since having the amount equal to 0 is our true base case. So, that call will return true. However, the recursion still continues, and on just to the left of that, both of those cases in lose it turn out to be false. So that one is false. But what happens to the case above it? Well, you might remember that the last line of the code is return use it or lose it. And since one is true, that's enough to make the case above it true. And similarly, the true case kind of crawls back up the tree, making the case above that true and the call above that true. So, overall, the function will return true, just like we expected. This is a pretty versatile algorithm strategy for whenever you want to choose several objects from a bigger group. And you might find some opportunities to use this strategy on some of the problem sets of this chapter, or for writing your own code. Good luck!